Neelakantha Bhanu Prakash, the world's fastest human calculator.
The fastest human calculator in the world.
4 world records and 50 Limca records.
Mathematics is said to be the language of our universe. From tiny atoms to massive galaxies out there, all elements communicate and express themselves through this language. And living creatures are no different. Every bit of our complex ecosystem and our day-to-day life is wonderfully woven, governed, and explained through the language of mathematics. By mastering math, we can understand our environment and surroundings, survival and civilization in a better way. Join me on this journey in exploring the beauty of mathematics and finding how this can be of practical use to me, you, and everyone else. It might not be so obvious at first, but we make a lot of decisions in life. And to think that we can solve them all mathematically doesn't seem so intuitive, right? Like how my director had to be pursued. Even though I had come up with a classical example to discuss LPP today, he wasn't really convinced.
Bhanu, I've been meaning to ask you something, actually for a long now. This linear programming video that we are going to do you really think it's a very practical and relatable problem that we are trying to solve? I mean, personally speaking, to be honest, for me, it doesn't seem like quite practical.
Linear programming is a very prevalent problem which exists in the world around us. Dealing with constraints, dealing with limitations, and understanding and creating equations out of it to solve for real life problems, that's exactly where linear programming problems are used all along. In fact, they're all around us. There's so many places where we use linear programming as a methodology to understand and solve for or optimize for a solution.
I mean, I haven't come across any problem yet, like at least I could relate to.
You'd be surprised. In fact, last week when we were buying beverages for our team, I solved for a linear programming problem to get to what we wanted. In the morning, my director and I encountered a usual yet confusing scenario. He had to buy coffees and teas for a couple of his colleagues. There were 10 of them in total. 4 of them liked to have coffees and 2 wanted teas, and the rest were okay with anything. Now my friend had only budgeted rupees 1000 in total for this activity, and each coffee cost rupees 100 and each tea cost rupees 80. He had to make a quick decision here on these numbers. And irrespective of his final decision, I believe this is very much an ideal LPP situation.
Okay, but I still don't get how this is a LPP problem.
Well, in linear programming problems, we attempt to find the ideal solution to problems with various constraints. Constraints like each person's preference in this case, which is whether you want a tea or a beverage, and another constraint here, which is the budget, of course.
But like, where are these problems really applicable in a general sense?
So LPP is applied. So LPP is applied in a wide array of problems, and the most common problem of what LPP solves for involves the general problem of allocating limited resources. Which is, if you're a government, how do you allocate your resources? If you are in an industry, how do you allocate your resources? How do you optimize to minimize cost? How do you optimize to minimize any quantity for that matter? And this is the best way to create competitive activities, and more importantly, finding optimized solutions.
Okay, but
It's ready. Time to shoot.
Hello math enthusiasts, I am Neelakantha Bhanu, the world's fastest human calculator, and let's continue talking about the linear programming problem, or the LPP. Let's come back to my original classical example. Imagine we are handling rice imports for a country called Utopia. We can only receive rice through 2 channels, ships and planes. While ships are cost effective, they take 15 days to deliver. And planes, They're faster, but extremely expensive. So this is quite a realistic problem you would face if you were importing rice to Utopia. Let's say, for each kilo we receive via ships, we pay $50, and for every kilo we receive via air, we pay $100. In real life cases, we would have to import a fixed amount of rice within a set budget. So let's assume that in this case, we need to purchase, as Utopia, to feed our individuals 60,000 kilos of rice with our budget of $5 million. Also, we have an urgent need to replenish our rice stock within 10 days. So we cannot order all the bulk through ships and save money. Now, how do we meet our requirements via both the channels without exceeding the budget we have? I know what you're thinking. Let the government solve for this problem. Why should I bother? Well, you should, because the method to solve this problem also applies in other real-life scenarios, like the beverage problem, where one needs to calculate the number of teas and coffees to buy within a budget and the team's preference. Let's look at how LPP can be used to solve this very problem. Let's assume that X1 and X2 are the number of teas and coffees respectively to buy for a team of 10 people within the budget of 1,000 rupees. The problem at hand is to minimize the total cost of beverages while fulfilling everyone's preferences. If we take all of this together, we get this equation known as the objective function. 100 multiplied by x1 plus 80 multiplied by x2 less than or equal to 1000, which is 100 multiplied by x1, which is the number of teas, and 80 multiplied by x2, which is the number of coffees, less than or equal to 1000 because that's the money we have. The equation for the choices of beverages will be x1 greater than or equal to 2, x2 greater than or equal to 4, which are the preferences and the choice. Finally, the total number of beverages that we have to buy will give us x1 plus x2 equals to 10, which means that we require 10 beverages in total. Solving these equations through graphs, we get two possible combinations: 2 teas and 8 coffees, or 6 teas and 4 coffees. Which one's more cost effective? You tell me. But also, can you find the relationship between this problem and the rice imports problem which we discussed earlier? Well, they are related. In fact, they are the same problem, the linear programming problem. Whether it's rice imports or choice of beverages, the ultimate motive of this problem is to find a solution within the constraints of the quantities which we have. Kilos of rice to be imported via ships or via air to Utopia are analogous to the quantity of tea and coffee which your team members might need. So we can apply the same method to solve the problem of Utopia. So let's assume that kilos of rice imported via ships and air to be S1 and S2 respectively. We know that we should get a total of 60,000 kilos of rice anyway. So S1 plus S2 is equal to 60,000. Also, our budget cannot increase and exceed more than $5 million. So optimizing for the cost, we get our objective function to be 50 multiplied by S1, which is $50, multiplied by S1, which is the number of kilos we import via ship, plus 100 multiplied by S2, which is $100 multiplied by the amount of kilos we import by air, the total of it, which is the total spend, less than or equal to $5 million. What are we solving for here? Is to import as much rice as we can with the budgets we have as quickly as possible to Utopia. Plotting these equations on the graph, we get S1, which equals to 20,000 kilos, and S2, which equals 40,000 kilos. These are our optimal solutions, meaning we need to import 20,000 kilos by ship and 40,000 kilos by air to meet the demand of 60,000 kilos and stay within the budget of $5 million while not pissing off the citizens of our country. These examples we explored were simplistic versions of real-world problems which have more variables and more constraints. Real life is way more complicated and is rather never two-dimensional. And so, the constraints, the variables and equations involved also get complex. Yet, the approach of the linear programming problem remains the same. Here's another daily problem that essentially needs LPP to resolve. A fitness enthusiast needs to consume 120 grams of protein every day and keep the fat consumption under 25 grams. Let's make the following assumptions, which are in fact close to the real life problem. Protein is consumed only from whey and eggs, and all the fat intake comes from eggs alone. Every scoop of whey has 30 grams of protein and no fat in it. But every egg has 6 grams of protein and 5 grams of fat. The cost of each scoop of whey is rupees 100 and the cost of each egg is rupees 6. Also, the total cost of consumption should not exceed rupees 400 per day. In this scenario, what is the optimum consumption of whey and eggs so that all the conditions are met? Stay tuned to our channel to know the solution to this problem. Fascinated by the world of maths? Subscribe for more application-based math content. Want to get 4 times quicker and better at mathematics? Check out the Bhanzu's experiential math learning courses. Hope you enjoyed watching. Until next time.